Hi everyone. Today we're going to show a follow-on demo from the previous OMEC demo, which showed that you can take any DPDK application and migrate it to use AFXDP without having to rewrite your application. All you had to do was pass an EAL argument called --vdev that would essentially transition your PMD backend from ICE or whatever PMD was being previously used from DPDK to the Linux native driver that is then using an AFXDP based PMD. What we also showed last time was the OMEC UPF being deployed in a Kubernetes environment by leveraging the SROV device plugin and the host device CNI. This all meant that we were able to launch our OMEC UPF in Kubernetes without modifying the DPDK application to use anything other than the AFXDP backends, and it also meant that UPF or that pod was privileged. So what we're going to show today is if we migrate to the AFXDP device plugin and the AFXDP CNI, we'll be able to actually launch our OMEC UPF with very few privileges, but essentially it'll be unprivileged. And that's the goal for today. But before we launch into the demo, let's just take a moment to discuss what the AFXDP device plugin and the CNI are doing. The AFXDP device plugin will essentially provision and advertise networking devices to Kubernetes that can be used for AFXDP based NetDevs. The CNI then manages, the transition of that NetDev from the host network namespace into the pod network namespace, and it's also capable of setting some ETH tool filters where needed for the for filtering traffic to an AFXDP socket if that's something that's of interest. One of the most important roles of the AFXDP device plugin is that it actually manages the loading of the BPF program on the NetDev. And by removing the need to load the BPF program from inside the pod out to the AFXDP device plugin, we are able to essentially reduce the privileges that our pod needs in order to launch and use AFXDP. So the thing that our pod needs to be able to create an AFXDP socket and use it is essentially a reference to what is called an XSK map. And this XSK map is tied to the BPF program when it's loaded onto the NetDev. And the AFXDP device plugin keeps reference to this map when it loads the BPF program on the NetDev. When our pod comes up, it uses a Unix domain socket that's mounted in the pod to communicate with the AFXDP device plugin to essentially perform a handshake and request the XSK map file descriptor. Once the AFXDP device plugin verifies that the pod is requesting, a file descriptor for a map to a NetDev that actually belongs to it, it will send the file descriptor over UDS to the pod, and the pod is able to start up, create an AFXDP socket, and continue to execute the DPDK application. It's important to note that this whole handshake is all integrated into the AFXDP PMD, so there's nothing extra for the application to do. Okay, so let's dive straight into the demo now. So the first thing we are going to do is launch the AFXDP device plugin. And if we just check that everything, I just have a tail running on the var log log essentially that gets generated when the AFXDP device plugin gets loaded. We can see it's doing some configuration by checking various bits on the host, retrieving pool configurations for the devices. It's essentially adding a couple of devices to the pool based on criteria that was defined in the AFXDP deployment specification, and it's initializing the various pools, and it's getting ready for kubelet, essentially trying to allocate something from the pool for pods that request using the FXDP device plugin. So the UPF that we're going to launch essentially has a few differences from the original DPDK UPF. We're just going to have a quick look at the YAML file here. Essentially, it's using the same CNI based configurations or network attachment definitions. But from a pod point of view, I just built a separate image for the DPDK OMEC UPF that's using the device plugin versus what we were using with the SROV device plugin. And they're setting up the same init containers. The main difference I want to draw your attention to here is the capabilities. So in the original DPDK UPF demo, the pod was, or the container in the pod was fully privileged, but here we're reducing the privilege set to typically you would only need netraw and IPC lock if you were trying to launch an AFXDP DPDK application that uses huge pages. But the OMEC UPF itself does some worker thread pinning to specific cores, and for that reason it requires these additional two privileges. We'll try and run the same demo with test PMD just after this and show that we only need IPC lock and netraw rather than sysnice and sysresource as well. So let's go ahead and launch that OMEC UPF. Okay, it's just it's starting the different containers and pulling images. And if we actually check the device plugin logs, we'll be able to see that originally we pretty much stopped somewhere here where we saw that the pools were ready to get allocation requests from kubelet. Here we can see an allocation request come in for one of the net devs, and actually we can even see the second continuation of that same allocation request, and essentially on the device plugin it initializes a Unix domain socket that's listening for new connections. You can see here part of the handshake happening, and eventually we'll be able to see an XSK map FD being sent for that specific netdev, and the XSK map, I guess more so the XSK map associated with that netdev. And again, you'll see that for the second interface as well, where there should be another handshake for the second interface requested by the UPF. So essentially at this point, if we enable port forwarding, apologies, if we export our cube configuration and enable port forwarding, and we go back to here and we refresh, we'll be able to see our pipeline is up and running. There's no traffic going through yet. We haven't started that, but let's try and add PDRs essentially to the application first. And this process takes a little bit of time to complete. So if we have a look, we can see that the PDR count is incrementing while that process continues to insert the PDRs into the OMEC UPF. Again, it just takes a little bit of time to complete, so we just have to wait a few more minutes to get up to the 200k rules. Okay, so now we can see the 200k rules have been inserted. Let's go ahead and start traffic. And we're just gonna quickly run the package in. And we can already see that there's some level of traffic passing through the UPF here. So 1.37 million packets per second, traversing the various parts of the pipeline, including PDR lookup, passing through GTP decap, QER lookup, going into FAR lookups, as we can see, and all the way further down the pipeline to the route lookups, and eventually being sent on their way. And that's really it from the OMEC UPF point of view. So let's just go ahead and tear down let's stop traffic first. And let's go ahead and tear down the UPF. And what I would like to show next is just a very simple test PMD pod that's going to be brought up. It's also going to be using two netdevs, same as the OMEC UPF was. And essentially we're going to see that it's going to be brought up with just two capabilities, netrun, IPC lock. I've created a script that will essentially generate the right command line to run test PMD by detecting the different netdevs that have been allocated to the pod. And let's go ahead and have a look at that in action. So let's just start with creating the test PMD pod. It's a pod called DPDK. If we can see, the test PMD container is started. Let's try and get a command line into that test PMD container. So if I run the script to generate the right command line, it generates it into a file called testpmd config.sh. which essentially configures the different VDEVs and the AFXDP sockets. So let's go ahead and run the test PMD script. And I actually run the test PMD application here with a log level of debug and the AFXDP PMD to show the two handshakes happening as part of the startup process for the test PMD application. We didn't have to do anything special, and we can see that test PMD comes up and runs as expected with the reduced privileges. That's really all I wanted to show, folks. Thank you very much for your time. And if you have any questions, obviously, please feel free to reach out to me at any time. Thank you.